Okay. So, good afternoon everyone, and till yesterday's class or till previous class, we were discussing about the deflection of beams using double integration method and the Cowell method, right? So, in that, if you have any question, any doubt, I have shared the handouts using the canvas, and there is one tutorial which is going to come on that. Three, four problems I will ask from that. Okay. So today we will start with another one new concept in case of material, which is very, very important. That is two-dimensional stress problem. Okay. Two-dimensional stress problem. There is a module allocated in your syllabus for studying two-dimensional stress problems. So what is actually two-dimensional stress problem? Okay. So basically, you see, two-dimensional stress means you have learned two-dimensional stress. Okay. So when we see the behavior of any element in a two-dimensional space, not in the third dimension. Okay. So two-dimensional stress means in x direction and in y direction. Let's say x direction and y direction, or x direction and z direction. In some cases, you will see z direction is taken as vertical, y direction is taken as the perpendicular direction to z. Okay. So let's say we are assuming that we will try to understand the space in a two-dimensional space. Okay. And when we talk about two-dimensional space problems, first let us try to understand 2-3 examples. Okay. For typical things you encounter in your solid mechanics, or going forward you will be encountering in your structural mechanics. So first thing we have discussed, if you remember, that is the case 1 I have shown here. That is the axial tension or compression. Okay, axial tension or compression. So you see what is happening because of axial tension and compression. Actually, you see, when there is an axial tension, so what is the stress you are getting? So because of the axial force, you are getting a stress, let's say, in the longitudinal direction, axial direction, right? So now, if you think that because of this axial stress, sigma x, at every point in the material or every cross section, only there will be sigma x, you are making some mistake. Okay, so if I take any cross section, let's say if I cut this like this one, okay. So if I cut the body like this under the axial stress or axial force, and I take a section something like this, let's say I take a section something like this, then you will observe that on that cut section, which is the inclined section, okay, there will be existence of not only vertical stress or axial stress, you will observe there is stress like shear stress also coming. So, it is very important to understand the stress condition in an inclined plane, okay, or in any cut section. What is the stress of stress along the plane and perpendicular to the plane? So, if I cut the section like this, along the plane there will be a stress condition, and perpendicular to the plane there will be a stress condition. So perpendicular to the plane means wherever is the plane, 90 degree. To that plane there will be a direction which is at 90 degree. Okay? And perpendicular to the plane, if I take, then you will see there will be a normal component of stress and there will be a shear component of stress. So you see, typically when you are taking the bar in axial tension, in that case also, what you are getting, you are not only getting only axial stress like sigma x in an inclined plane. Rather, you are getting a normal stress sigma x, okay, and also you are along with that, you are also getting one stress. So this is the condition of axial. Now let's go to the next condition. That case number 2, if I understand, if you try to understand, this is the case of biaxial stress. So what is biaxial? Axial means single direction. So biaxial means two direction, right? So biaxial stress condition, let's say, if you take a vessel like this, or if you take a thin cylinder kind of pressure vessel, then what happens? The forces come in this direction as well as in the circumferential direction, right? So along the longitudinal direction there will be stress, along the circumferential direction there will be stress, right? So if you consider this kind of stress condition, then you see what is happening. There is stress in this direction and there is stress in this direction. So if I perpendicularly take two stress condition in two directions, in x direction and y direction, and if I take a small element, let's say for this cylindrical specimen only, let's say if I take, so this is subjected to this and this, and in between, let's say there is a small element, something like this. So if I consider a small element over here, then I need to study what is the stress condition in that small element. And also, if I take an inclined plane in this element, then what will be stress condition at this plane? Okay? So that is also important. So have you understood what is the biaxial stress condition? Each and every stress condition will come into picture. Okay? Later on you will understand step by step. Okay? And you will see that how to find out the normal stress and shear stress in these conditions. Okay, so always you will see, because of, so these are normal stresses, you see axial, normal single directional axial stress or bidirectional axial stress, both cases these are normal stresses. However, you will see, because of the normal stress also, the shear stress is coming into picture in the element. And if you take an inclined plane, there will be a stress which is shearing in nature, as well as there will be a stress which is normal to the plane wherever we are taking the incline. Clear? Now come to the third case. So third case is general case. So general case is very important case, and this case is the common case and general case in a two-dimensional stress plane. Okay? So you see, this is actually a beam, right? This is actually a simple supported beam. Now this simple supported beam, when it is subjected to a load P, then what happens? You have seen that there is a bending stress coming, right? So there will be extension of the element. So there is a linear kind of tension kind of thing is coming. So sigma x is coming over there, and also there will be shear stress coming in a beam, right? So if you consider a small element over here like this inside the beam, so you can see both the normal stresses as well as shear stresses are existing in the element. And you need to study this state of stress. Okay? So this state of stress, so being subjected to both normal and shear stress. This is the normal stress, this is the shear stress. And shear stress, if you can see, so these two are making a anti-clock direction, so this will be making clockwise direction. What is that? That is actually complementary shear stress. Because if there is a shear stress existing in two planes, so there will be complementary shear stress in the other two planes. Right? Now, second case is a shaft. What is the difference between that one and this one? That one is subjected to a biaxial stress condition. So thin cylinder, let's say you are putting oil inside it. In a thin cylindrical vessel, you are putting oil inside it. So oil will try to come out, right? Ooze out through the circumferential and on the top direction. Okay? So pressure will be created. So there will be this directional stress, this directional stress. What is the difference from this? This is also a thin kind of cylinder. What is the difference between that one and this one? So this one, if you can see, this is a shaft and it is subjected to torsion. So you are twisting in opposite direction couple, you are twisting, right? So when you are twisting it, you see, you are twisting it as well as you are pulling it. So you are making a pull. Let's say you are having a cylinder, you are making a pull as well as you are trying to twist. In a mechanical system commonly comes, right? So in such case, again, this kind of stress condition will prevail. And you see, there are normal stress and there are PCR stresses coming in. Have you understood? So you need to understand what will be the state of stress in such kind of element, as well as if you cut any section, inclined section, through that small section, whatever you are taking out, in that plane, what will be the stress, state of stress? What will be the normal stress? What will be the stress? Okay? And that study we will be doing in next 2-3 lectures. Okay? Now, what is plane stress? So you see, definition-wise, a state of stress on the edges of a square or rectangular element. So you can see everywhere I have taken a rectangular, small rectangular element. The state of stress on the edges of a square or rectangular element in which there are no stresses normal to its place is called plane stress. So what is the plane stress condition? So you can see, plane stress condition means a two-dimensional stress condition. We are assuming in such a way that stress condition is remaining in an element which will be either in rectangular shape or in a square shape, and the stresses will be on the edges or perpendicular to the face. Okay, so you can see this is the stress, and along the edges there are stress. However, you see there is no stress perpendicular to this. Is there any stress condition over there? So this is actually normal. So there are no stresses normal to its face. So this is the face of the event. So there is no stress coming out of it. This is actually called plane stress condition. And this is what typically is called two-dimensional stress condition. So sometimes it is defined as plane stress condition, sometimes you tell it as two-dimensional stress condition. Have you understood? Now, after this plane stress condition, let us move to the next part of understanding the analysis of plane stress. And while you do the analysis of plane stress, few terminologies and few notations you need to be very clear. And you have also learned about these notations while you have studied the first chapter on basics of stress and strain. Okay? However, again we revisit. So, two terms very important. One is X plane and another one is Y plane. Okay? X plane and Y plane. Very important to understand. Okay? Because you see, sometimes problem becomes complicated if you do not understand what is the plane exactly about. Okay? So you see, plane perpendicular to x-axis. So if I take two axes something like this, x and y. Okay? So if I take axis like this, then and I take an element something like this, let's say this one, rectangular element or square element like this. So plane perpendicular to x-axis, that will be called as x-plane. So what is x-plane in that case? So this is my x-axis, right? So the plane, this plane is perpendicular to x-axis. So this plane will be called as x-plane. Have you understood? So the plane which is perpendicular to x-axis will be called as x-plane. And the plane, which one is perpendicular to y? This plane is perpendicular to y, right? So this will be termed as y plane. And you see, they are little different than the axis notation system. X-axis, the plane which is perpendicular to x-axis, we will call it as x-plane. The plane which is perpendicular to y-axis, we will call it as y-plane. These two definitions are important, because many competitive examinations questions are asked through this x-plane and y-plane notation. Okay. Next is sigma x. So what is sigma x? Sigma x is normal stress on x-plane. Okay. So that means along the x-axis, whatever stress is there. So if I put a stress along the x-axis, so this will be termed as sigma x. So sigma x is acting on which plane? And if I do a sigma y, then where it is acting? This acting in the y. It is perpendicular to or along the y-axis, or the plane is the y. Clear? So x plane, y plane, sorry, sigma x and sigma y, they are the rotations of normal space. And then you see there are two spaces, tau xy and tau yx. Very clearly these two terms need to be understood. What is tau xy? Please see the notation, tau xy. So tau xy is the shear space on x plane. Shear space on x plane. Which is the x plane? Which is x plane? This one is your x plane, right? So shear space on x plane along y-axis. So you see, x plane is perpendicular to the y-axis, right? So this will be termed as tau x. Have you understood? Clear? So the shear space which is occurring along the x plane, that subscript will come first, and along the axis where it is acting, that will come second. So what will be the space in this axis? So if this is this way, then what will be in this way? This will be this way, right? So it will be tau xy. This will be also tau xy. Because shear space, so two planes, two distant planes, there will be shear spaces. And because of this tau xy, there will be a complementary stress coming. So on which plane it will be acting? It will be acting on y plane. So where it will be acting? So it will be acting in this plane, right? And I have told you the rotation wise, or while drawing it, these two arrows should be in the should be facing each other, because you see this is doing a clock thing, so you must have the anti-clock thing to come there, right? So this one is which plane? This is acting along which plane? This is acting along y plane and along x-axis. So this will be tau y x. Got it? This will be direction wise this way. These are very important. I have seen many of the students do mistake while just writing these four things. Where do you point out sigma x, where do you point out sigma y? How do you write tau xy and tau yx? Okay? Now you see the notation wise and this wise. So sigma x, if it is there, then there is a sigma x here, sigma y, so there is a sigma y over here. So if the normal spaces are positive, then we will take it is tensile, or we can take tensile sigma x as positive. Okay? And if it is compressive, then we will take it as negative. Okay? On the other hand, shear stress in this derivation, whatever we will be doing, in that we will consider shear stress is positive when the sense of rotation is clockwise. So if I take this rotation, this rotation is clockwise or anti-clockwise? Rotating in this way, right? It is rotating in this way, clockwise. So this shear stress, that is tau xy, will be in this case positive. Okay? This is the convention we are following in this derivation, and I have followed the convention from Timoshenko. Okay? Timoshenko's convention. Okay? You can also take clockwise as negative, doesn't matter. But accordingly you will have to put all the values in your formulation and calculation. So tau xy is positive. On the other hand, you see tau yx, this is what is happening? Tau yx, clockwise or anti-clockwise? This is anti-clock. This convention wise we will call it negative. Okay? And you see this tau xy must be equal to tau yx in terms of what? In terms of its magnitude. However, in terms of sign, they should be equal and opposite. But in terms of sign, it will be opposite. Okay? So tau xy should be equal to tau yx. Is it clear? Have you understood? Any confusion about this conventions? Whatever we'll be using? Because see, if you do not understand this, then next part you will not be able to understand. Okay? So remember tau xy and tau ix, they are complementary shear spaces, right? And when they are complementary shear spaces, then tau xy will be equal to tau yx and we get minus. So sign wise, value wise they are equal, and obviously they will be equal and opposite in sign. Okay? So I can replace tau xy with tau yx. I can replace tau xy with tau yx with a changed sign. That's all. Because they are complementary. Clear? Next you see, now you have to understand state of plane stress. This is very, very important. Okay? State of plane stress, and this is the simple. What should I say? That is resolution of force along different planes or different axes. Okay. So like the force resolution you do. So you remember. So I just ask you one question. This is x-axis. This is y-axis. Let's say I have a force. Let's say F over here. The angle of inclination is theta. Then what is the force along x-axis? So it is F cos theta. Okay. So if I take a drop at vertical, then it is F cos theta, and along this axis is F sin theta. Right. So this is the thing we will be using. Simple resolution of forces along the planes we will be using to understand the state of plane stress in a small rectangular or square. Okay. So if I try to do that, then you see, suppose I take one element something like this. So let's say again I redraw. So let's say I am making some element like this, and then it is subjected to, let's say, both the normal stresses as well as shear stresses. Both normal stresses as well as shear stresses. So both normal stress means, so there is a stress which is sigma x acting. So sigma x, you see, sigma x is the stress, right? So sigma x is acting along the plane. And which plane? X plane. And sigma y is acting along y plane, right? So the resultant of the distributed total force will be equal to sigma x, right? So if I multiply sigma x with the area of the x plane on the plane where it is acting, okay? And that is a very thin plane it will be, because we are considering two-dimensional case. So if we take a very small area, which is the area of the x plane, and multiply the space with that area, what I will get? I will get the force. And I can resolve that force along different axes. That's what we are going to do while doing the state of, while understanding the state of plane. Okay? So let's say we are having sigma x in this direction. So you are having sigma x right in this direction, which is acting in the x plane. And then you are having sigma y, let's say like this, sigma y. And these are assumed here in this derivation. These are assumed what? Tension and compression. These are assumed tension because they are acting outward, right? So sigma x is tension, sigma y is also tension. And what we have assumed? We have assumed that tau xy should be positive, and that positive sense is when it is clockwise. So the tau xy is, I have on this plane there is a tau xy. So obviously there will be this way and this will be here as tau xy, right? Here there will be tau xy. So you can see there is a tau xy, there is a tau xy. So where the tau ix will come? Tau ix will come in anti-clockwise direction, so tau yx will come in this direction, and this way tau yx will come in this direction. Is it clear? Again I am redrawn it to understand or understanding. Okay? Is it now clear? That sign, whatever you are drawing inside, it should not be inside, it should be outside. It should be outside. Okay, shear stress cannot happen in the inside of the element. See my notations? I have drawn it outside. Okay, it cannot, if you draw it inside, then it is wrong. Okay? So outside. And then you see, we will try to find out what I said. You will have to understand what is the state of stress at a particular plane. So you have taken a rectangular element or you have taken a square element, right? And the state of stress at a particular plane, let's say the plane which is making an angle, let's say phi, which is making an angle, let's say phi, with which plane? This is which plane? These are very important. Please remember these terms, whatever I am telling. Okay? It is making angle with which plane? X plane. So these will be the terminologies which will be coming in the problem. That if the problem is now tells you that the angle is made with y plane, then you have to convert from the y plane to x plane angle. Because we are deriving the expression using the assumption that angle of the plane is being made with what? With the x plane. So if you are given in the problem that angle is made with the y plane, then you have to convert it to the angle with the x plane. How do you do it? To subtract 90 degree minus that. Clear? Have you understood? So if I take a small portion cut out, so I have taken this one, right? So my phi can change, right? My phi is 0 means I am here. My phi is 1 degree means somewhere here. 2 degree, 3 degree like this. When phi is 45 degree, I will come in here, right? Gradually, if my phi increases, I will go there and I will reach over here. So when my phi becomes what? When my phi becomes 90 degree, I am going from x plane to y plane. Have you understood? So phi the value of phi may change from 0 to 90 degree. Correct? Next is, if I now take up this part of the section, so you see that's what is being depicted over here. So what you will get, this will be a triangular section, right? So let's say I take up a portion of it and this is what is your section. Correct? Now tell me what are the stresses acting or what are the forces being acted on this. So you see, let the area of x space of the element is dx. So x space means x plane, right? So if the area is dAx, then what will be the force in the x plane? The force in the x plane obviously will be what? Stress sigma x into dAx. Why I am taking differential term? I am assuming that the element is very small and the thickness of the element is very small, two-dimensional stress problem. So I am assuming that area of the face is a very small amount of area, that is dAx, right? Differential term. Okay. And what will be if the area of the y face is dAy, then what will be the force? Sigma y dAy. Correct? Anything else will be acting on this? So there will be shear stresses coming, right? So what are the shear stresses coming? So this stress, you see, this will be coming in this direction. So there will be a tau yx over here, and there will be what in this direction, right? So there will be tau xy coming. And what is tau xy? And this is actually my angle phi. Have you understood? This is my angle phi. From here I am cutting it and bringing it over here. Clear? Have you understood? Now you tell me, what will be now the stress. So phi is the angle for any plane inside the element taken in the anti-clockwise direction from the x plane. This is what is very very important. Okay? Anti-clockwise direction from the x plane we are taking. Okay? So this definition wise, because see in your derivation, whatever you will take, whatever formulation you do, you cannot do multiple derivations. So accordingly, you have to put the formulation correctly while solving the problem, and you have to put the signs properly. Okay? So phi is taken in which direction? Anti-clockwise direction from the x plane. So I am taking anti-clockwise direction from the x plane. Clear? So force system, have you understood? So is this tau yx whatever I have written, it is correct? Yes, sir. No, it is the space. So in this also I should multiply for the force dAy, and what will be the stress here? Tau xy into dAx. It is acting in the x plane, right? Clear? So this is actually the force system to which this element is subjected to when there is a plane inclined to a phi angle which is being taken in the anti-clockwise direction from the x axis, x plane it is being taken. Clear? So under this force system, now you see the first example, the actual thing I have shown you. In that you have seen that there is an inclined plane, and we have to understand the state of stress in that inclined plane. What is happening? What will happen in that inclined plane? Right? If you can understand what will happen in the inclined plane, then you can very easily find out for any other plane, right? So at a phi angle, whatever is happening, you can find out. You can find out what will happen for phi is equal to 0. You can find out what will happen for phi is equal to 90. You can find out what will happen for phi is equal to 45, phi is equal to 30, phi is equal to 50. And that will give you state of stress in the elemental body at each and every plane. Isn't it? Correct or not? So considering that, if I now try to find out the state of stress in this inclined plane, so we will observe that there will be a stress along the plane will be coming, and there will be a stress perpendicular to the plane. So the stress along the plane, so there will be a stress along this plane, and there will be a stress perpendicular to this plane. Okay, there will be a stress perpendicular to this plane, and this perpendicular to this plane, whatever the stress is coming, that we are denoting as sigma n, and the stress which is coming along the plane in that inclined plane, we are assuming it as tau. Have you understood? Is it clear? Got it? Now you see, suppose my x-axis, suppose this is the angle phi. So where is my x-axis? So if I try to draw an x-axis from this, so x-axis is horizontal like this. This is my x-axis, not x-plane. This is my x-axis. Where is my y-axis? Y-axis will be this one, right? So if you study the geometry of this, simple geometry, and if you take the alternate angles and find out, then what you will get this phi angle, whatever you are getting over here, that should be equal to होगा कि नहीं होगा? It will come like that because that is perpendicular x-axis, y-axis, that is the inclined plane which is making an angle phi. So the stresses which are perpendicular to the axis and along the stress axis, that perpendicular thing, that perpendicular stress to the inclined plane should be making an angle phi with what? With x-axis. Clear? So now, if you can resolve, now you see that if the area of this plane, if I assume that norm an, so the force will be sigma an into dn, sigma a into dn, and what will be tau? The force due to tau will be tau into dA. What is dAn? EAN is the area of the inclined plane. Clear? Now the next part is very simple. You have to resolve the forces along what? You have to resolve the forces and find out what is happening along this sigma and what is happening along this now. So if you can resolve the forces like this, then you can easily find out what will be the state of phase in the what is called x-axis. In the planes of inclined planes, which is making an angle phi. Okay. So I think today's class will stop here already lunchtime, and this resolution of forces we'll understand in the next class. It is a simple resolution of force, and you will require some little bit of trigonometric identity, like trigonometric formula like sin square phi plus cos square phi is equal to 1. Then what is the value of sin 2 phi? 2 sin phi cos phi. Then cos 2 phi is equal to 1 plus 2, 1 plus cos square phi. Sin 2 phi is equal to. So these are the typical identities we will be requiring. Okay. So these formulas you will be requiring. 2 sin phi cos phi is equal to sin 2 phi. Then cos 2 phi is equal to cos square phi minus sin square phi. Then cos 2 phi is equal to cos square phi minus 1 minus cos square phi. That means cos 2 phi is equal to 2 cos square phi minus 1, or cos 2 phi or sin square phi is equal to half of 1 minus cos 2 phi. So these kind of trigonometric identities will come into picture, because you will see from the phi the equation whatever you will be deriving, that will be changing to a value of 2 phi. That will be changing to a value of 2 phi. That means if phi is equal to 90 degree, you will get expression in terms of 2 phi, in terms of 180 degree you will get expression. Got it? So that part we will understand in the next class. So here trigonometric identity, all this trigonometric identity, whatever trigonometric formulations you know from your 12th standard, that you need to remember. Okay, otherwise you will not be able to solve this kind of problems. Okay, so I think I stop here today, and next class we will take up from there. Resolution of force in the triangular equilibrium. Okay, stop.